Welcome to the Getting Started with GeoStudio video series. This tutorial introduces how to use the Sigma W product of GeoStudio 2012. This tutorial video has been designed to help walk new users through the basics of setting up a simple stress and deformation analysis in Sigma W. So, if you are new to Sigma W and are not sure where to start, you have come to the right place. The main topics that will be covered in the tutorial will be how to create an analysis in Sigma W by using the Define view to set up the analysis, the Solve Manager to solve the numerical analysis, and the options available in Results view to gain a deeper understanding of the analysis. So, let's get started. Here are some results of a stress and deformation analysis completed in Sigma W. The objective of the analysis was to determine the settlement of a circular water-filled tank. The upper 5 meters of soil have different properties than the underlying 20 meters. The tank is 10 meters in diameter with an applied pressure on the ground when the tank is full of 40 kilopascals. Since the problem is symmetrical about the vertical center line of the tank, the problem will only include half of the tank, and we will conduct an axisymmetric analysis. An axisymmetric formulation considers the stresses in the x to y plane, as well as the circumferential stresses, and the profile you create is rotated around the axis of symmetry. We will start on the GeoStudio Start page, where you can create a new project, open an existing project, or click on the appropriate links to view examples, tutorial videos, or engineering books for each GeoStudio product on our website. We will create a new project and choose to create the project using the default International System of Units. If preferred, a blank document can be created with imperial units at this point. Once our new project is created, the Key in Analyses window is opened, where we can add a title to our analyses tree, add an author, or add comments for future users. Now we are ready to add the Sigma W analysis to our analysis tree. We will add a load deformation analysis. Here, we can change the name of our analysis, as well as change our analysis type if desired, but we will keep the load deformation analysis type. We can also add a description about the analysis to help future users. The drop-down boxes are available if there are previous analyses or results for the initial stress or poor water pressure conditions for the start of the analysis. For this analysis, we will simply leave these drop-down menus to none. The Convergence tab can be used to change the convergence settings for the analysis. We will keep the default settings, but more information on these values can be seen in the engineering book for Sigma W. The Time tab can be changed if desired, including an increase in the number of time steps or duration, but will be left with the default settings of 1 time step, that is 1 second, to simulate the addition of the load in 1 step. The Advanced tab also has the option to include a body force in all steps, or to adjust the fill elevation with foundation settlement, but these are not required for the purpose of this tutorial. You can use the zoom options along the bottom bar of your screen, or under Set Zoom, to change the view of your analysis, either to the extents of your domain, or to the extents of the work area page, or simply zoom in or zoom out. We will simply zoom into our drawing page, as we don't have our domain defined yet, and then take a look at the drawing scale of our analysis. We will go to Set, Units and Scale, and here we can see the units that are being used in our current analysis. Here is where we can change our units if desired, but I will keep the default of seconds and kilonewtons. The problem extents boxes can be used to help modify the scale of the analysis. Changing these values can change the view of your analysis so that the entire domain remains on a single page. We will toggle off the Calculate Max Extents option and change our minimum x coordinate to -8 meters and our y coordinate to -6 meters and our maximum x coordinate to 40 meters and our maximum y coordinate to 30 meters. This automatically adjusts our scale values to accommodate these extents. We will toggle on the Calculate Max Extents again and fine-tune our horizontal and vertical scale values to ensure a 1-to-1 aspect ratio. Since we are conducting an axisymmetric analysis, we will toggle on the axisymmetric option. Here, a value of 360 degrees indicates that all results will be calculated relating to the full circle around the axis of symmetry. In this case, we will simply simulate the results of one of the sections by changing this value to 360 degrees divided by 2 times pi, or 57.29578 degrees. As you can see in the background of the page on my screen, there is a grid already activated. You can go to Set, Grid, to turn this grid off or on, activate Snap to Grid, or change the grid spacing. Now we are ready to create our domain. We will start by adding axes to our working area to help visualize the drawing extents of our domain. This is completed by going to Sketch, Axes. Here you can also change the names of the axis titles, as well as the X and Y axis extents. We will set the X-axis extent to be from -5 meters to 40 meters, and the Y-axis extents to be from -2 meters to 15 meters. You can also change the increment size of the axes labels by toggling off the Auto Increment Size button and changing the increment size for each axis. The approach to use when developing a numerical model is to determine the geometry, assign materials, assign boundary conditions, and fine-tune the finite element mesh. Let's start by creating a domain. Here we have a sketch already completed of the water-filled tank on the 2 soil layers. To create our modeling domain, I will go to Draw Regions and draw my 2 soil regions following the sketch of my problem. Here, points will automatically be made wherever I use the left mouse button to click on the working area. Once a region is created, I can draw the next region, or I can use my right mouse button or the Escape button on my keyboard to stop the Draw Regions command. Next, we will add the materials to our analysis. I will go to Draw Materials and click on the Key In button to open the Materials Define window. I will add a new material, give my material a name, and enter my soil properties for the linear elastic total stress model. In this case, only the stiffness modulus and Poisson's ratio are required. Next, we will add a second material for the lower soil layer. There are 2 options that can be used when adding the second material. The first is to simply use the Add button again to create a new material, or the Clone button can be used to clone the first material. Then I will adjust the soil properties to represent the second layer. Now that my 2 materials are defined, I will go to Draw Materials and add the materials to each region representing the soil layers. The next step will be to define the boundary conditions. I will go to Key in, Boundary Conditions. Here we can see by default there are 3 boundary conditions already defined for stress-strain scenarios. You can also create your own boundary condition to represent the pressure of the water-filled tank on the ground surface. So we will add a new boundary condition and apply the vertical stress of 40 kilopascals onto the ground surface. Here, the negative sign indicates that the pressure is going down onto the soil surface. You can also change the color of the boundary condition by going to Color, Set. To apply the boundary conditions to the domain, we will go to Draw Boundary Conditions and choose the fixed X boundary condition to apply to the left boundary representing the vertical axis of symmetry in this analysis. This is the only boundary that we want to allow vertical movement or settlement, but we still want to restrict any lateral or horizontal movement. For the bottom and right boundaries, we will assume that the movement can be fixed in both the X and Y directions. Now we are ready to apply the tank pressure boundary condition to the line under the location of the tank. Here, we require a point to be added to the domain to ensure that the boundary condition does not extend past the actual location of the tank, so we will click on Draw Point. Now this point has become a part of the domain, and we can add the tank pressure boundary condition to the line representing the contact between the soil surface and the bottom of the tank. Now that the geometry has been drawn and the material properties and boundary conditions have been applied, we are ready to review the finite element mesh and make any necessary adjustments. We will click on the Draw Mesh Properties button and see that the meshing algorithm has a global element size of 2 meters with a meshing pattern of an unstructured mesh of quadrilaterals and triangles. We will keep the 2-meter element size, but we will change all regions to include a meshing pattern of the structured quadrilateral elements only. You can also hold down the Control button on your keyboard and click on multiple regions to apply changes in the meshing properties of multiple regions. We will decrease the size of the mesh for the 2 soil layers directly below the tank, as these layers are expected to be affected the most by the pressure applied by the tank. We will choose to change the element size to half of the global mesh element size, or 1 meter. We will also apply secondary nodes to these regions so that the 8 noded elements are used, while the remaining elements will be kept with the default 4 noded elements. The number of nodes in your finite element mesh will affect both the size of your file and the amount of time required to solve the problem, so it is important to only use secondary nodes when necessary to obtain a better solution. Now, we will make sure that the analysis is activated in the Solve Manager window and solve the analysis by clicking on the Start button. Once solved, the window will automatically change to the Results view instead of the Define view. By default, Y total stress contours will be shown. Contour options can be changed by going to the Draw Contours window. Here you can change the coloring scheme of your contours, add or remove a legend, change the increments of your contours, or add new contours to the Contour drop-down menu, such as Material Properties or other results information. The Draw Contours Labels button can be used to add or remove contour labels by simply clicking on the contour where you want the label painted. Labels can also be removed by clicking the label again. The main objective of the simulation was to determine the vertical settlement of the water-filled tank. We can go to Draw Vectors and choose to view the displacement as either a deformed mesh or with vectors, and the magnification of the displacement on the profile can be adjusted here. The maximum displacement is also summarized in this dialog box. You can turn on or off this displacement visualization along with other visualization tools in the View Preferences toolbar, either along the right side of your screen or under View Preferences. Another way to view results is to create a Moore circle. We can use the Draw Moore Circle button and choose a node or Gauss region below the tank where we would like to know more information about stress results. A Moore Circle window will appear, showing the stresses for that node or element Gauss region. This information can be copied and pasted into another program or printed from this window. We can also draw a graph of the lateral displacements under the tank. I will go to Draw Graph and add a new graph to the window. I will select the displacement, X displacement versus elevation, and choose a vertical profile below the edge of the tank. Here, you can either drag and drop a box around the desired nodes, or hold the Shift button on your keyboard while drawing a line through the desired nodes. Now we can see the X displacement along the vertical path we chose. I can use the More button to copy the graph image so that it can be pasted as a picture into another program, the graph data as tab delimited columns which can be pasted into another software like Microsoft Excel, or exported as a separate comma delimited file. I can change the visualization of my graph by clicking on More Options. Here I can customize the labels on my graph, change the scale of my axes, rotate my graph so that the elevation is on the y-axis, add or remove a legend, change the style of my lines, or change the font of the text on my graph. There are also other options that can be used to view result information within the Results window. For example, you can view result information, which outlines the result information for each geometry item, such as the total stress applied to a node below the tank. The View Report button can be used to develop a report of the input data and will open the report in an HTML format. This gives you all of the information regarding the input data, geometry, and other information from the analysis. Note, if at any time you are unsure in your understanding of the dialog boxes, you can simply click on the question mark in the top right corner of the dialog boxes, use the Help tab, or use F1 on your keyboard to access the online help. If at any time you would like to view the engineering book for the product you are using and do not want to return to the GeoStudio Start page, you can simply click on the Home button on the online help. We have now reached the end of this introductory tutorial. Note that not all of the powerful features of Sigma W 2012 have been used or discussed here. Further information on each command can be found in the online help, supporting documentation for Sigma W, as well as in other tutorial videos of the Getting Started with GeoStudio video series. Thank you for watching.